Hello, everyone. Today we're going to be continuing with stoichiometry. Today we're going to be focusing on the volume aspect of it. I know this unit section says calculations with both particles and volume, but what I'm doing is I'm following the order of the class sets, okay? So class set 1, which is what you did on Friday, is focused on moles and grams, okay? Class set 2 does that exact same thing, except now it adds a volume piece to it. Okay, so there is a volume portion. Okay, so that's the next thing that's being added. So I'm going to be focusing on volume today and not on particles. Okay, so I'm just going to give you that heads up. Okay, so this first piece where it says calculations with particles, I'm going to skip that part. Okay, I believe we're going to get to it eventually, but the work doesn't focus on that, so I'm not going to focus on that. Okay, I want to try to summarize things as best as I can. Okay, so let's start here. So stoichiometry calculations with volumes. So when we were on Friday, when we were looking at the chemical equations, we looked at the coefficients in front of the numbers as moles. Okay, so you could say that this is telling us that 2 moles of hydrogen and 1 mole of oxygen give you 2 moles of water if you react that. Okay, and that's easy to understand. But when we're talking about gases, things can get a little confusing. Okay, because if you say the same thing, if we convert, instead of saying moles, we say liters, which is what they say here. You have 2 liters of hydrogen plus 1 liter of oxygen, and that makes 2 liters of water. Okay. Some of you may get confused with this because you might say that how can 2 liters of something and 1 liter of something else, you mix it together and you get less than what you started with? Okay. How can you have 2 liters of this, 1 liter of this, but you only get 2 liters of water at the end? That's like if I told you to mix 2 gallons of water and 1 gallon of orange juice and mix it together in a container, that you're only going to get 2 gallons of something. That isn't intuitive. Like that doesn't seem feasible. But when it comes to gases, just know that it is. Okay, that can happen. It might sound confusing. It might seem weird, but just know that that does happen. And even with liquids, it's not necessarily a 1-to-1 ratio. So, for example, let's do rubbing alcohol. You look at your rubbing alcohol. It might say it's like 70% isopropyl or 90%, whatever it is. That container, it's part alcohol and part water. If you mixed a liter of alcohol with a liter of water, you might say you're going to get 2 liters after you mix them together because 1 plus 1. But that isn't necessarily true. You're going to get a little less than that, actually. You're going to get like 1.98 liters, okay, something like that. It's not 1-to-1. And there's a reason behind it, there's a science behind it, but it's beyond this class. That is very beyond this class, but just know that that is a thing. So just because you see 2 liters of one and 1 liter of another, 2 plus 1, you might say that should give you 3, but know that with gases that isn't true. So I just want to make that clear, okay? That this might seem confusing, this might seem like how the hell is this possible, but it can happen, okay? With volume, it can happen, okay? So put that out there. But I want you to just, instead of focusing on moles for this section, focus on the volume aspect, okay? Volume of a material is proportional to the number of moles that you have of it, but only when it's in the gas phase. So this is where we got to start paying attention to this part of the chemical equations, okay? So if it's G, it's a gas, and that's when these things are applicable, okay? So just let's start paying a little more attention to that aspect of it. And now let's do some quick examples focusing on the coefficients. So these examples we're going to look at real quick is going to focus on converting just based off of the coefficients. Okay, so we're not going to do any like hard setup calculations because we're not converting units yet. When we start converting units, we're going to have to do that. But for now, let's just practice using the coefficients. So it starts us off with this. We want to know how many liters of oxygen are produced when 12 liters of NO2 are formed. Okay, so this is telling us we have a decomposition equation. We know how many of this we made, okay? NO2. We know how many we made of this, We want to know how much oxygen that would be, okay? That's what this question is asking us. Looking at the recipe, if we follow this recipe exactly, we should get 4 liters of NO2 if we follow the recipe exactly. What the problem is telling us is that we have 12, okay? So what you want to do is you want to figure out how much did we scale up this recipe, okay? Because you can scale recipes up or down to make more or less of something that you need, okay? So we made 12 liters. The recipe only makes 4. If we made 12, that means we tripled the recipe, okay? That's what we did. We tripled it. And where do I get that? And you can do 12 divided by 4. 12 divided by 4 is going to give you 3, okay? So we tripled this recipe. We scaled it up by a factor of 3. That's what you can say, okay? So now that we know how much we scaled it up, let's look at how much oxygen you make. So if we followed the recipe exactly, you would make 1 liter of oxygen. Okay, you would make 1 liter of oxygen. But we tripled the recipe, so we need to triple this coefficient, and then 1 times 3 is going to be 3. So the answer to number 19 is B. Okay, and I answered this question just looking at the coefficients. I just used the coefficients. Okay. 20. What volume of methane? Methane is CH4, just to make this clear. Methane is CH4. Okay, so this is what they're talking about in the problem. To completely react with 500 milliliters of O2. 500 milliliters is the same thing as half a liter, just so you're aware. So just to keep it consistent so that you don't get confused, this is 0.5 liters of oxygen is what they're saying. Okay. So we know how much oxygen we have. What we want to know is how much methane we need. First thing we got to do is balance the equation, okay? So this is practice from something we've done in the past. So let's do the hydrogens first. You have 4 over here, you only have 2 over here, so we need to double this, okay? And now we have 2 oxygens, 4, now we need 4, so there should be a 2 here, and then 1 and 1, okay? And now it's balanced. So now looking at our equation, we're looking at methane and oxygen. So we're just looking at the left side. So ignore the right. We are not focusing on the right side. We're just focusing on the left. Okay. For every 1 methane, we need 2 oxygens. Okay. So there's 2 ways you can look at this. You can say you need double the methane in oxygen, or you could say you need half of the oxygen in methane. Okay. So we have half a liter of oxygen. We only need half of it in methane form in order to get the exact ratio. So 500, we only need half of that in methane, so this would be 250. And this comes from the coefficient. You need double the amount of methane in oxygen because for every 1 methane, you need 2 oxygens. So this comes straight from the coefficients. So you have half of the oxygen in methane form. So just divide your volume amount by 2 and you can figure out how much methane you have. Okay, 1 more and then we'll get to the manual calculations, which is what I want to focus on. Oh, okay. All right, cool. Don't want to delete. Okay. How many liters of water will be created by reacting 8 liters of hydrogen with a sufficient amount of oxygen? So when you say this, so sufficient amount of oxygen. What that means is don't worry about calculating how much oxygen you need. Pretend you have an infinite amount of it. You have enough that you need to do the reaction. Okay, so when you see this type of stuff, that's what they're telling you. Okay, so we're focusing on water and hydrogen. Okay, so this is what we're looking at. Okay, so they basically told us ignore oxygen. We have a sufficient amount of oxygen. We're not worried about the oxygen. We want to know how many liters of water we're going to make if we have 8 liters of H2. Okay. So looking at the coefficients, looking at the recipe, for every 2 liters of hydrogen, you're going to make 2 liters of water. So it is 1 to 1. So for every liter of hydrogen you have, you're going to get that same amounts in water. They have the exact same coefficient. okay? Because they have the exact same coefficient, there is no calculations we have to do. It's going to be the exact same number. So if we have 8 liters of hydrogen, we're going to make 8 liters of water, okay? And we know that because, again, the coefficients are exactly the same. Okay, there's no scaling, there's no nothing. It's the same. It's 1 to 1. It's a 1 to 1 ratio, you could say. All right. Okay. Now let's get to the meat and potatoes. Okay. So this is going to be our example equation. So this is the equation we're going to be looking at for the rest of these problems. Okay. We want to know how many liters of nitrogen would be needed to produce 3 moles of ammonia. Okay. So just like the class sets, you have 2 units. So we want to go from 1 unit to another. But I told you should always start with moles first. So we're going to be calculating everything in moles first. Okay. So nitrogen and ammonia is what we're looking at. Step 1 to all these problems, okay, same thing as class set 1, class set 2. Step 1, I told you, is to set up your ratio. Look at what you want to convert from and where we are going to, okay? We want to go from ammonia to nitrogen. They told us how much nitrogen, how much ammonia we produce. We want to know how much nitrogen we need. So step 1 is to set up your ratio. And they do that here. In your ratio, what you are converting to goes up top. What you are converting from goes on the bottom. We want to go from ammonia. We have 3 moles of ammonia. We want to go from ammonia 2 liters of nitrogen. So since we're going to nitrogen, nitrogen should be up top. And it is. Okay, you have nitrogen up top. We are coming from ammonia, and that's why ammonia is on the bottom. Okay? And then you look at the equation, the numbers that you put in there are based off of the coefficients. Nitrogen has a 1 in front of it, or it has nothing in front of it, which means it's a 1. Okay, so that's where the 1 comes from. And then the ammonia has a 2, and that's where the 2 comes from. Okay, so now you got the ratio. Boom. Step 2 is to just multiply it out, which is what this piece is. Okay, that's what this piece is. After you multiply it out, you will end up with your moles of nitrogen. Okay, so they do this whole thing, they multiply it out, and they end up with their moles of nitrogen. The next piece is the conversion piece. So for class set 1, when you were going from moles to grams or grams to moles and vice versa, after you finish this piece, this step, this conversion, you would then convert it into grams. But instead of converting it to grams, we are instead going to convert it to volume, okay? So previously you had to look up these things atomic masses to do this step. You don't have to do that with this. Instead, you are using the volume piece, the thing we learned from the last unit. 1 mole is equal to 22.4 liters at STP. Okay, this is where you have to remember the mole calculations. Remember, we have moles to mass, moles to particles, and moles to volume. We are focusing in this case on moles to volume. So we calculate how much moles of nitrogen we have, and then this last step, this right here, is the conversion to volume. This is saying for every 1 mole of something, you have 22.4 liters. They finish the multiplication out, the units cancel, NH3 cancels, and then moles cancel, and you're left with liters of N2. Okay, that's how that works out. That's why we set it up the way that we set it up. Okay. This is a particle calculation, so I'm actually going to skip this piece. Okay. So in terms of what's new, there really is nothing new, which is what I want you guys to realize as you do this over and over and over again, okay? So for Friday, we focused on moles and grams. We're adding volume, but the calculations are the same. The only difference is different unit, but the setup is the same. Everything is exactly the same, okay? Everything is exactly the same, but instead of converting to grams here, in this case, we're converting to volume. Okay. I think you guys will start to find this to be tedious and simple eventually, as you do it over and over again. But I want you to see, the more you do it, the more you see the repetition, and it's the same. So even though we're adding volume now, it's really no different than what you did on Friday. Okay. So 23 is this is a particle problem, so I'm going to skip this since we're not doing particles. Okay. This is something we can do here. Okay. We want to know how many liters of oxygen would be needed to combust. This is a combustion reaction. This hydrocarbon, and we are producing 5.5 moles of water. Okay. So we want to go from water to oxygen. Okay. That's what we are comparing. We're told how much water we make. We want to know how much oxygen we need. Okay. We want liters of oxygen. We're told water. We want to find oxygen. Step one, always set up your ratio. Step one is your ratio. So look at the problem or look at the chemical equation. We are converting to oxygen. So oxygen needs to go up top. We are coming from water. So water needs to go on the bottom. Look at the chemical equation. What number goes with which? So 163 goes with oxygen. 110 goes with water. Okay. So it doesn't matter how crazy and ridiculous the numbers get, as long as you follow the step by step, you should be good no matter what. Okay. So now we have our ratio. Good. Step two, multiply it out. How many moles of water do we have? We have 5.5. We want to go to moles of oxygen. So I'm just going to multiply this out. I'm not going to write the units because I have limited space. But this multiplication step is going to take us to moles of oxygen. Okay, so you multiply that out. Let me get my trusty calculator. Okay. 163 divided by 110, and we get 8.15. Okay, so this is moles of O2. So we almost answered the question. It says how many liters of oxygen gas would be needed to produce 5.5 moles of water. We found how many moles of oxygen we need. So then the last step, step three, I'm going to delete everything because I need the space. Now we need to convert it from moles to liters. Okay. So we have 8.15 moles of O2. Okay. Times. Now we need to convert it to volume. This is where you got to remember from the mole section, in 1 mole of gas at STP, you get 22.4 liters. Same thing applies here. What you are converting to goes on the top. What you are coming from goes on the bottom. We are going to liters, so the liters needs to go up top. We are coming from mole, so mole needs to be on the bottom. And then you will see that your moles cancel out, and you're left with just liters. Okay, so you multiply this out, 8.15 times 22.4, and you get 182.56, which rounds up to be 183. Okay, rounds up to be 183. I will do one more example, and I will call it. I don't want to make the video too long, and it's just calculations. I will not be doing a volume example in the class set just because there's only two. There's problem D in number 1 and A in number 2. So there's not that many of them. I want to give you the opportunity to practice them. So I'm going to go through just the examples in here. I'm not going to go through an example in the worksheet. So how many moles of carbon dioxide would be needed to produce? Now, how many moles of carbon dioxide would be produced if 2.24 liters of gas reacted? So this told us how many liters of oxygen we have. Can we do this strictly in gas form? Because if everything is in gases already, then we may not need to convert anything. Let me see if I can apply this trick here, because it's a trick I want to show you. Give me one moment. Okay, so the trick I was thinking of can't work here. What I was trying to see is, since they're both in gases, is there a step we can skip? But there's no step we can skip. Okay, so we want to go from oxygen to CO2, but pay attention to the units. They want to know your final answer needs to be in moles. Okay. So to answer this question, we can either convert the volume to moles now, or we can do that at the end. Okay. I'm actually going to do that at the end just to change it up a little bit. Because they're both in gas form, I can convert liters of oxygen to liters of carbon dioxide. If this was solid CO2, I wouldn't be able to do this. I would have to convert to moles in the very beginning. But because they're both in gas form, I can do that at the end instead. So as always, step 1, set up your ratio. I'm going to set up the ratio in volume form, even though it's the exact same thing. So what this is saying, we are going from oxygen to carbon dioxide. So CO2 should be up top and oxygen should be on the bottom. Okay. And this is liters of both. This is liters of both. You can think about it in volume form or liters. So same thing I'm mentioning is this piece right here. Remember how they were talking about you can read this as liters. Okay, you can read the coefficients as liters instead of moles. We can do that in this case because they are both in gas form. We can do that here. So I can change this to liters instead of moles. But the process is the same. So no matter how you look at it, it's the same. We're still setting up our ratio. What we are converting to goes on the top. What we are converting from goes on the bottom. We are going from oxygen to CO2. So this is our ratio. Step 2 is to multiply it out. So we have 2.24 liters of oxygen times 114 divided by 163. And this comes out to be 1.57. This is liters of carbon dioxide. This does not answer our question because they asked for us to find it in moles. So then the last step is to convert that to moles. So we have 1.57 liters of carbon dioxide times, and now we're going to use that same equation or ratio from earlier, except we're going to flip it. Remember, what you are converting to goes on the top. This time we are converting to moles. So then mole goes up top. And then for every 1 mole, it's 22.4 liters. Okay. Put that in your calculator, and you get 0.07, okay, which is A. Just round it, okay? So that's it for this piece. In terms of the setup is the same as Friday. It's the same, just step one, ratio, step two, multiply it out. And if there's a conversion step, then step three is to do the conversion, okay? In this case, for the first one, they want you to balance the equation first, okay? For this, just look at, I look at the hydrogens first, okay? So this one has how many hydrogens in it? This one has 52. So then what times what is 52? You get two of them over here. Just divide that by 2. And so you know that this needs to be a 26. I'll help you out with that. So this is 26. If you make that a 26, let's make this a 25. Okay. Leave that as a 1. And then the last piece, so that should be, that's 50. 50 plus 26. Yeah, because 25 times 2, 26, divide that by 2, and this should be 38. Okay, that's your balanced equation. 1, 38, 25, 26. That is your balanced equation. And from there, you can answer the rest of the problems. Okay, again, the setup is the same. If you guys have any questions, any issues, any concerns, please feel free to reach out as always. Again, I won't go through any examples in here just because I want to give you the practice with the volume, and it's the exact same scenario as last week. Okay, so take care, guys. Happy Monday. Hope you had a good weekend. And yeah, best of luck. Take care. Be safe.